Okay, so let's just begin with this question. Okay, not a question. Hmm. So you have some point P, random point lying outside of a circle. I'll call this circle omega. Also, goes without saying, if you have any questions, feel free to unmute or put in chat. That's fine. Unmuting is preferred, obviously. And you have this one segment which intersects the circle at 2 points, A and B, and at two other points, C and D, another segment. So I need to show that PA into PB equals to PC into PD. Like, this seems like an unmotivated length for one reason. Like, you can take any two random segments and this length relation holds. Like, why should this be true? But the thing is, it's basically just similarity. So since ABCD is cyclic, like since ABCD is cyclic, we have angle PAC equals to 180 degree minus angle CAB, which is equals to angle BDC, or you can say it equals to angle BDP. So you have that this angle is equals to this angle. Similarly, this angle will be equals to this angle. You can say by symmetry, or you can just write the angles as both of them are fine. So this gives you that triangle PAC is similar to triangle PDB. Notice the thing, like it's not PAC PBD. Like if it was PAC is similar to PBD, it will imply parallel. Like it will imply stuff like this, that these two things are parallel. But it's the other way around. Like it's AC and DB. So like it's switched. So we can write this as PA over PC equals PD over PB. So you get PA into PB equals to PC into PD, right? And notice that we can do it for any 2 points. Sorry, any two segments. Okay, so let's take a segment which is the tangent. Like what I do is I have this one segment PAB and the other segment PC1 D1 PC2 D2. What I'm doing is I'm taking C and D very close to each other, like progressively closer and closer to each other. Like maybe something like this eventually comes C and DN. Like I take them close and close and close until they're just one point, which is the tangency point. So let's call this point, bro. It's hard to draw lines. Right. Let's call this point T, which is both C and D. So what is your guess? PA times PB is equals to, in terms of length, which involve T.
PT square,
Okay, why?
because C and D just collide. So PC into PD will be essentially be PT into PT, which is PT square.
Yes. So this will be PT square. Okay. Like some people might say that why can't it be PT? First, you notice that like the dimension here is like meter square if you take length in meters, or like degree 2. But PT just says degree 1. So obviously it can't be that. And what Lavish said that PC times PD, right? C and D basically become equal to T. So this is one side thing. It's not related to power of point, but one thing that you should remember. So if we write the line TT, it means tangent at T. Obviously, with respect to some circle that is being in the conversation. So, like if I'm talking about circle omega and I say that T is some random point on omega and consider the line TT, it just means tangent at T. Okay, like this is used very often. Like sometimes you'll use some theorems which will give you you have to consider like PP cap AB. Then what does PP really mean here? It just means tangent at P intersection with line AB. So this nice thing that you should care about. And using this definition, look, the way you can define tangent is the point at which a line intersects the circle at 2 points. So like when both the like a line always intersects the circle at 2 points or 0 points, right? So like one point is like tangency point. It's like very unique. So why talk about a unique point? We can just define tangency point as like line intersecting the circle twice. So we can define tangency point as point at which a line intersects the circle twice. Usually the 2 points are distinct, like A and B. But when they become equal, equals to T, we can just select TT. And that also makes like intuitive sense, right? We can denote a line by AB. So why not by TT? So I just gave like a bit definition to that. What does that actually mean? Yes, degenerate cases of Pascal and Desargues. I didn't want to say that because people might not know Pascal and Desargues here. Okay, you can ignore that. That's irrelevant for even in my opinion. Anyway, so let's move on to our discussion. So now we have that for some random circle and some random point P, if I draw a tangent T and take some random chords, I have some nice length relations. Okay, what other nice line can I take in this figure? Like a nice line which is sort of unique.
A line that passes through the center.
Yes.
Yeah,
So we have a
yeah.
circle, right? So let's just introduce its center, O. And let's take this line PO. This will intersect at 2 points called X and Y. So from what we were doing, we know that this is equals to Px times Py, right? So I can write Px as Po minus Ox times Py as Po plus Oy. If the radius is r, like this length is r, then this length is also equals to r, right? So I get Po minus r times Po plus r. So I get Po square minus r square. So notice that this thing for a fixed circle, like for a fixed circle, Po square minus r square is a function of P. Right? Like it just depends on P because O and R are fixed, right? So we call this power of P, power of point P. It's nothing else. It's just a function in P. Okay. Like if I just have told you in the beginning of the class, like, hey, so I'm telling you about some random function, power P equals to OP square minus R square. Like, what is this? Random. Where does this length come from? It's very random, right? No motivation. But this at least makes you feel motivated. And why we are introducing this function? Like, there's clearly significance of this function, right? Okay, we did all this for a point outside the circle. What about a point inside the circle? So let's take P here and I take AB and CD here. Like this is also equals to like PA into PB, right? From our arguments before. For any A and B lying on the circle such that PAB are collinear. Anyway, so can you tell me if PA into PB equals to PC into PD here? Is it true? Can someone tell me?
Yeah,
Why?
because triangles PAC and PDB are similar.
Right. So notice that this angle is subtended by the arc BC, right? Is equals to this angle. And you can do these two angles are equal. Similarly, these angles are also equal. So we get triangle PAC similar to triangle PDB, just like earlier. So we have all that same thing. Like if you take a line passing through the center here as well, you'll get the same result. Power of P is equals to OP square minus R square. Right? Notice that when P lies inside, OP is less than R, so OP square minus R square will be negative. So power of P is negative. When P lies outside omega, power of P is positive, right? Because PO will be greater than R. But what happens when power of P equals to 0? Like, what is the case left? When the point lies
Point
on the circle,
lies on the circle. Yeah.
let's take point P lying on the circle. So we know power is 0 by this formula OP square minus R square, right? Because now OP is just equals to radius. But how do we to our this visualization of power? Like this is the strong visualization which led us to everything, right? So what we do is we consider some line passing through P and intersect it at the circle. Let's call this point, which is equals to P only, A, and let's call this as B. So now power of P equals to PA times PB, but A is equals to P, right? So what is PA? PA is just 0. So power is 0. Like this is like a degenerate case. This is what you will call degenerate, usually. Like to get the idea. I'm not defining degenerate cases, but this is sort of the idea.
Yeah.
Sorry, can
The
you repeat?
imagination.
Wait, can you repeat? Okay, I assume that's not a question. Anyway, so now we have discussed power. So to summarize, okay, one more thing to keep in mind. Like I'm saying power of P equals to 0 or something. In problem, you might have more than one circle, right? So it's a bit troublesome to like mention the circle, like power P with respect to omega. Like why not just add omega into the notation somewhere? So we write it as power and omega in subscript of P. So this means power of
I'm
point.
saying that the imagination.
Aritra, your voice is breaking. Can't really hear you. Sorry. Maybe you can type. Anyway, so until he types, this notation means power of point P with respect to omega. So this thing encloses everything about the function that we just discussed. Okay. So is power of one point with respect to a circle clear to everyone? All the three cases and what it means. Like this is just equals to OP square minus R square, which is equals to PA times PV, where AB is a chord. Like can people type yes or raise hand or something for those who it's clear?
Yeah, clear.
Okay. Other people would be nice to get some responses. Okay.
Yeah.
Okay. Okay, that's good. So now we know. Okay, I should have asked this earlier, but for those of you who know PowerPoint from before, try this question. Can you see my screen? Like, what do you see? OneNote or something else?
It's okay.
Wait, what do you people see? OneNote only, right? Okay, fine. For those of you who know PowerPoint, try this problem. Wait, where is the problem? Buffer problem. For those of you who don't, I don't suggest trying this problem because it's a hard problem. I mean, hard if you don't know PowerPoint, obviously. So you have some triangle ABC. Uh, D is a point such that BD equals to CD. Let P be a point on line BD such that AP equals to BP. Define Q similarly. Okay, I expect people to know what this means because it's used very commonly. If you don't know, please ask. Define Q similarly. Prove that the line PQ passes through a fixed point.
D is not fixed on line BC, na?
No, it's a random point. Like it just means D lies on perpendicular bisector. Okay, right. So I'll wait a minute for people to take screenshot or something, or if they want to write down. But I'll not discuss this problem much. We'll just discuss PowerPoint. All right. So now that we have seen power with respect to one circle, what happens if there are two circles in the image? Like suppose I have circle one omega 1 and some circle to omega 2. Like, how can I relate power of one circle with another circle? Right? It feels very weird. And if we see this intersection point, A and B, both of them have power 0. Like, power of A with respect to omega 1 is 0, which is also the power of A with respect to omega 2. Right? Same goes for B. So, like, maybe I can find all points P such that power of P with respect to omega 1 is equals to power of P with respect to omega 2. Okay. So let's try to do this. Okay. Let me, right. I don't know any geometric proof for this. The proof I know is by coordinate geometry. Well, motivate by coordinate geometry is nice as well in this case. Like, it's not at all horrible. And I think this everyone should listen, even if they know power of point, because it tells a lot of ideas about bashing if people are potentially interested in it, or just like how to set up nice things. Especially for IOQM, this idea is very useful. Like, people set up coordinates and use that a lot. So, see, we need to find all P such that O, okay, let's say the center of omega 1 is O, 1, and center of omega 2 is O2, and radius is R1, radius is R2. So we need OP1 square minus R1 square equals to, yeah, it's the same proof as in ECMO, but I also want to tell motivation about how to set up the coordinates. Equals to OP2 square minus R2 square. Right. So notice that firstly, these distances OP1 and OP2 are squared. And what is the distance formula? It's like root A1 minus A2 square plus B1 minus B2 square, right? But if I square this, like if I consider D square, the square root goes away. And this thing is not as bad to deal with if you choose the points cleverly. So this is where the intuition or like choosing reference carefully comes in. So what I'll do is, a very naive way to do this would be okay, sorry, I wrote this wrong. Bad that nobody pointed out. It should be O1P and O2P. So let, this is a very bad way of doing this. O1 be, let's say, some A comma B, O2 be some C comma D, and P be equals to some X comma Y. Like, you'll still be able to do this thing, but it's just much better. Do you see how many variables we have? 1, 2, 3, 4, 5, 6. Like,
Zero.
a person who is not experienced might think that this is the only way to do this, but I'll tell you a clever way. So what you can do is, I'll fix O1. Okay. Like, it doesn't matter if I rotate the image or like translate it, right? That's fine. Nobody cares. Like, the image remains the same. So I'll just set up the origin at O1. And I'll take O2 on x-axis. I can do this because I can rotate stuff. So this is my x-axis. I'll take some point O2 here such that O2 is equals to A comma 0. And I'll now take P equals to x comma y. So what are the points that I have now? O1 is 0 comma 0. O2 is some A comma 0. And P is x comma y. I have now just three variables. Rest all are zeros. And zeros are obviously nice in computation. It's like, do you see the clever way? With the naive way, which everyone would be doing, we had six variables. Bad. But now we only have three variables. Okay, in some cases, especially when you're doing barycentric, it's fine if people don't know what barycentric is. You might want to keep the degree of everything equal, so this is bad. But at least for Cartesian coordinates, like coordinate bash, which we are doing right now, it's much more convenient to have more and more zeros you can. Depends from question to question, but at least for like IOQM problems, RM or INMO, you shouldn't really worry about these things. Like, have as many zeros or ones you can. Okay, so now uh, O1P will be, O1P square will just be x square plus y square, and O2P will be just x minus a square plus y square. So I have x square plus y square minus r1 square equals to x minus a square plus y square minus r2 square. I can expand the perfect square and write it as x square minus 2ax plus x square. Oh, sorry, plus a square. So cancelling out the square terms, I'll get r2 square minus r1 square minus a square equals to minus 2ax. So this implies x equals to r2 square minus r1 square minus a square upon minus 2a. Notice that r2, r1 and a are all constants. They are fixed. So this is some constant c, right? So I have x equals to c, which means the locus of all points with power of p equals to power like power with respect to omega 1 equals to power with respect to omega 2 is a line perpendicular to x-axis. See, another reason why this picking of coordinates was nice is because once I get x equals to c, I know that it's a line perpendicular to x-axis. But now I also know what the x-axis is. It's the line joining the two centers, right? Now, in the original figures, even if I like now rotate back and translate and all, I know that the this line where the powers are equal will still be a line perpendicular to this line, like something like this, right? So this is why picking the coordinates nicely is an essential skill. Not essential for people who just do synthetic, but it's fine. I like doing bash. Anyways, so since we talked about power of A is same with respect to both circles, right? And so is B. So we know that A and B lie on this particular line. Let's call this line L. So we know A comma B lie on L. So we just know the line, right? If you know 2 points lying on a line, we know the line. So the power of all the so the locus of all the points such that their power is equal is the line which passes through the intersection. And this also proves that this line is perpendicular to the line joining the centers. Okay. There is a nice term for this. We call this radical axis of omega 1 and omega 2. So radical axis is basically just a line such that if any point belongs on the line, on that line, then power of p with respect to omega 1 is equals to power of p with respect to omega 2. So is this clear to everyone? I should create a poll because otherwise people don't answer.
Yeah.
Yeah, I'll create a poll. Except, am I the host of this meeting? Why can't I create poll? What? Huh? Okay, people just raise hands or something like if it's clear. I can't create a poll for some reason. Like raise hand, thumbs up, any reaction is good. Okay. 1/3 of the class answered. That's good enough. Okay, now let's move on. So let me think how to motivate this. Okay, so it's a very bad way of motivating, but it actually works. Okay, I wouldn't say it's bad. It's just okay. Can you scroll? What part do you want to see, Gulshan?
Do you have any synthetic proof?
Not that I know of. Sorry.
Can you think about this?
I mean, I've thought about it.
When
That's
I,
why.
when I
What do you mean by A equals to C? Yeah. What part is not clear? Oh, if a beautiful journey has synthetic proof, I should also check it out. Thanks for telling that, Gapian. Yeah, I'll check it out. Did not know that. Gulshan, is it fine? Okay, cool. Also, if you're noting down things, it's not useful. Like you can find all this information in EGMO or ABJTG, I believe. And if you want, I'll send these notes as well. Okay. So when we had power of a point, we were discussing a point with one circle, right? And then we moved on. Then we saw how power works with two circles. And this led us to introduce radical axis. So now, continuing the same thing, let's try introducing, let's try seeing how radical axes work with three circles. Okay, so suppose I have three circles. Okay, I'm just taking all of them intersecting right now. Notice that power can exist, sorry, radical axis exists even if the two circles don't intersect. Okay, we'll see that after this thing. So let's call the circles omega 1, omega 2, and omega 3. This is the radical axis of 1 and 2. Let's call this L12. This is the radical axis of 1 and 3. Let's call this L13. And this is the radical axis of 1 and 2. Let's call this L12. Like, even in a very bad diagram, it looks like these three lines are concurrent at a point P. So this is like a guess. This is how you build intuition. That these three lines are concurrent at a point P. And wow, this is actually true. Like, radical axis of any three random circles is concurrent. Like, these circles are not special, I'm telling you. So, theorem, radical axis of three circles. Okay, by radical axis of three circles, I mean like pairwise radical axis. You take radical axis of two circles, then another two, and then another two. So you'll get three lines in total are concurrent. Think about how you would prove it for a minute or two. If anyone has done the proof, no need to tell me because it's, excuse me, not a very hard proof. So just think about it for yourself for 2 minutes. If you want to tell me, you can type in private chat, but yeah. I'll wait for a minute or so. Okay, at least type done if you are done with the proof or if you already know it in private chat. And you can ask me for hints on bubble problem if you have tried enough in personal chat. Yeah, difficulty of buffer problem. It's hard. Like, okay, I wouldn't say by contest, but it's hard. Like, not very hard as well. Like, it involves all the standard ideas. So nothing out of the box. Okay, one person wrote done.
Please don't give any spoiler, please.
No, I'm not giving spoilers. I'm just telling like it involves standard ideas. Like that's the point of this class, no? Like you already know what idea will be used in the problem. So you already have a spoiler. I'm not saying anything apart from that. Okay, so it's already been 2 minutes. We will discuss the proof. So see, you have to prove concurrency. What's the general idea of proving concurrency? Okay, also I decided that I'll do a lot of problems, like I took some 6, 7 problems, but it looks like we'll just do a PSS and do those problems in that. We'll not have much time for problems. So suppose you have to prove L1, L2, L3 concurrent. What I'll do is I'll introduce a point P equals to L1 cap L2 and show that P lies on L3. This is how I'll generally prove concurrency. So let's just do that here. Suppose I take radius of this circle and this circle and let them intersect at point P, right? So let's call this circle 1, 2, and 3. Omega 1, omega 2, omega 3. So I know P lies on radix of, okay, radical axis is abbreviated at radix. So it's nothing new. I have taught you that. Radix of 1 and 3. This means power of P with respect to omega 1 is same as power of P with respect to omega 3. And P lies on radix of omega 2 and omega 3 as well. Which means power of P with respect to omega 3 is same as power of P with respect to omega 2. So combining these two things, I'll get power of P with respect to omega 1 is same as power of P with respect to omega 2. So this just means P lies on radix of 1 and 2. So P lies on this line as well. So that's it for the concurrency. And P is known as radical center of omega 1, omega 2, and omega 3. Okay, so is radical axis and radical center clear to everyone?
Yeah, it's clear.
Okay. I get one yes. Yeah, Lavish, I know you're not even seeing the class, so it's fine. I know it's a yes for you already. Other people like raise hand or something or speak. It's good to get responses. If you want me to repeat any part, that's fine. Like just tell me what part though. Okay, Cindy said yes.
Question
Huh,
about the radical center. Like there like only exists a radical center when there are three circles together. Otherwise it doesn't, right?
you are saying that if three circles intersect with each other, right? Otherwise they don't.
Okay, that's the only case where there exists radical center.
Wait, let me close my fan. I can't hear. Yeah, can you repeat the question?
Yeah, so the only case where radical center actually exists is where three circles intersect together. Otherwise it doesn't.
Okay, no. So I'll have to discuss that. I was gonna discuss what happens when two circles don't intersect, radical axis in that case, and then we'll see radical center in that case as well. So I'll just answer your question in a bit. Okay.
Okay.
Any other questions? Ask quickly. I've turned on my fan. It's hot here. Okay. Uh, right. So what happens when two circles don't intersect each other? So what is the radical axis in this case? So I have someone O1, O2, right? So if we see the proof we did earlier, let's just take like O1 as 0, comma 0 and O2 as a comma 0 and xy is random point which has power equal with both of the circles. Then I'll get that x equals to this thing, right? So x is equals to r2 square minus r1 square minus a square by 2 minus 2a. So according to this, notice that nothing really cancels. Like nothing really becomes equals to. Okay, my point is x is a real number as long as a not equals to 0, right? Which means that radical axis must exist in this case, right? And it obviously does, right? Because maybe x is equals to like something like here. Some line perpendicular here I'll take, it lies outside both of the circles, right? So now, like, if I take some point P1 here, I know that power is negative for any P. Like, power of P is negative for any P on this random line, right? So sign is not an issue. And like, yeah, it just exists because X is a real number. And the line is literally just that. Like, take X distance from here and construct a perpendicular line. So a radical axis exists even if the two circles don't intersect. Let's just take a circle, another inside circle, another circle. What happens in this case? It still exists as long as the centers don't collide. Because that's the only case when X does not exist. If I take two concentric circles, then I have that center of one circle is 0, comma 0, but the center of other circle, which is a comma 0, is also 0, comma 0, which means a equals to 0. So in this case, x does not exist, right? So there is no radix. So unless the two circles are concentric, there is always a radical axis. So is this clear to everyone?
Above, you have showed that power of P will be negative. Won't it be positive because P is outside the circle?
Yes, thank you for correcting me. But the point being, like, it's of the same sign. Okay, the point was actually here. Like, where will the radix of these two circles lie? Like, it can't lie here because for every point on this purple line, power with respect to this small circle is positive, but with respect to big circle, it's zero somewhere, positive here, negative here, right? So it can't be something like this. Or at this line, like here, the power is negative for the big circle, but positive for small circle. So it should be like somewhere here or here. That was the point that I was trying to show with the sign. But the point is, as long as the two circles are not coaxial, radical axis always exists. Okay, now let's just see three random circles. Okay, I'm telling you for
What's
this case.
coaxial?
Can you repeat?
What's coaxial? Thing?
Oh, sorry. So coaxial circles. Circles with the same center. So something like this case. Like in this case, A is equals to 0 as well, right? When they have the same center.
Isn't that
So,
concentric?
huh?
Isn't that concentric?
Oh my God. What am I doing? Okay. It's been too long since I've been with terminology. Yes, I wrote correct here, but why am I saying coaxial there? Yes, it's concentric. I believe people would know concentric. Coaxial is something different. Never mind. Uh, you know this, right, Surayana?
Yeah.
Okay, fine. Yeah. Okay. So for this case, when two circles are like this, it makes intuitive sense that the radical axis will lie somewhere in between. Okay. Wait, is it always intuitive? And is it always true?
I have a question that how to construct the radical axis for two circles, or they are
That
not
we'll see after
concentric.
we do radical center thing. I'll tell you that. That I have in mind. Don't worry. Let me just think about one thing. Okay, let me just quickly check. I'm not sure about this thing. Like it looks false to me, but intuitively it looks true. So let me just quickly check.
Which counterexample are you looking for? I joined now.
So basically, like I'm seeing if there are two circles like this, the radical axis always lies in the middle of them, which slightly looks false to me, but I've never seen a counterexample in my life myself.
Like if it lies like you're telling that if there are two circles in this configuration, it always lies like in middle of the two circles.
Yes, that's what I think. But
Yeah,
I'm not
so
100% sure.
like in a radical axis, the tangents are equal. So if it lies on the left side, then the tangents to the circles will not be equal, and same with the right
Oh,
side.
yes.
It should be equal.
Yes, thank you. Nice proof. Okay, I should have probably shown that. So, yeah, if you have two random circles and you draw their common tangent and you take the midpoint of them, like let's say M is the midpoint. I got so then let's say the tangent intersects here at A and B. So you know that the power of M with respect to this small circle is MS square. And power of M with respect to omega 2 is MB square. Right? Since M is the midpoint, MA equals to MB. So
we
you'll
have
get
the radical
huh?
axis. These two
Your net is
circles.
bad, Ritra. I can't really hear you. So M lies on the radical axis. So obviously the radical axis will be in between the two circles. Thanks, Aaron, for the proof. Right. So now we are seeing like if you have two circles far away from each other, we have a radical axis between them. We exactly don't know where, but we know it's somewhere between them. Right. So now let's look at the radical center thing. So suppose I draw three circles here. I know that the radical axis exists, like it's somewhere like this, and somewhere like this. I can do the literally same proof and show that they're concurrent. Even if like two of them intersect with each other, and the third one is like far away, I can do the same thing. Like the thing is, radical axis exists for any two circles as long as they are not concentric. So the radical center must exist as well. So Sharayana, does that answer your question now?
Yes.
Okay. So someone, I think Aritra, I'm not sure who, asked this, how to find radical axis. I'm like assuming this question is geometrically in problems, there are different ways. Aditya, I did plan to do problems, but this is taking more time and I'm also enjoying this. So it's possible we might end up not doing any problems. But if you don't do any problems, we'll take a PSS question. How to find radical axis. So if the two circles intersect with each other, then it's obvious that this is the radical axis, right? If the two circles don't intersect with each other, I can take their common tangent, like this one and this one, take their midpoints, and this is the radical axis, as Aaron pointed out. This was not the proof I had in mind, but whatever. This works. But what about this case? When one circle is another other circle. Like here I can't draw any common tangents. I don't have what? Yeah, I don't have common tangents or the intersection points, right? So what I'll do is I'll construct some random circle, omega 1, omega 2, and this green circle is omega 3. Okay. I'll construct circles such that it intersects both of the circles. I know the radical axis is omega 1 and omega 3. It's this pink line, right? And I know radical axis of these two circles as well. Let's call this point as P1. So by radical center thing, like not by radical center, like P1 is radical center of omega 1, omega 2, omega 3, which means P1 lies on radax of omega 1 and omega 2. So I have constructed one point which lies on the radax. I can now construct the other point as well. Right? Like take some other random circle and do the same thing. So you get 2 points, so you can construct. Or another way of doing it is if you can find the center. Suppose this is the center and this is the center. I'll draw the line joining the centers, and then the radix is just the line perpendicular, passing through P through these lines. So this is how you can construct radix for these kind of circles. I don't think you'll ever need this, but just in case you do. So is this clear to everyone?
Yeah.
Yep.
Yes.
Okay, nice. Other people? Yes, no
This
raising
proof
hand.
will work for any two circles. This proof will work for any two circles.
Sorry, can you just repeat the first part of the question? What if for any two circles?
Yeah, if the circles lies outside to each other, then means
Arindra,
that
can you
take a
please
random
type your
circle
question?
and
I can't really understand it. It's breaking a lot.
yeah, okay.
Thank you. I'll wait for a minute for Arindra's question and then we'll move on. Okay, in the time he's typing the question, I'll do some new thing. Oh, this proof will work for me. Like this is not a proof. This is a way of constructing radical axis. Of two circles just lie inside each other. Like this will work for any two circles. Yeah, obviously. Like I just told you, like for other cases, it's easier to do radical axis by other ways. You can use the same thing for them as well. Okay, so let's move on to one thing that we had skipped. Suppose I give you two circles. I know the radical axis is this line. Suppose I give you another circle such that the radical axis is parallel. So omega 1, omega 2, omega 3. Like now I have that the intersection of these two radical circles does not exist. Okay, some people who know projective geometry and are very smart might say that it exists in infinity, but we are working with the real plane. So we're not doing any nonsense of that sort here. Uh, so yeah, also Ritra, if the circle has outside inside doesn't matter. Like try to do it on your own then. Like I told you method. Okay. So if the radical axis is parallel, like okay, firstly, where is the like how will the third radical axis look like?
Also parallel to those two.
Yes, because if it's not parallel, let's say something like this, then it obviously has an intersection, and this radix should also pass through this. So all three radix are parallel. Okay, now let's think about this. A radix is a line, like when does this case happen exactly? Radical axis is a line which is perpendicular to the line joining centers. So this means O1, okay, O3 and O2 are perpendicular to this line. And O2 and O1 are also perpendicular to this line. So basically like O1, O2, O3 are collinear. Because O1, O2 is perpendicular to the same line as O2, O3. And O2 is a common point. So the only way it makes sense is if all the three centers are collinear. So in this case, radical center does not exist. So this is an annoying case which sometimes happens and you'll have to deal with, but rest is fine. If you are using GeoGebra, it might look like it's parallel, but it's not parallel. And if you are using, okay, someone asked about buffer problem. And if you're using pen paper, It might look it's parallel, but it's not actually parallel. Like I'm telling you, it's through a fixed point. Unless you arrive at some special case in which it's parallel, but it passes through a fixed point. Okay. The only way it can be parallel is the triangle ABC is isosceles. Can you repeat radical center? I can give you a brief overview, but I'm not going over the whole thing. That will take too long. You can watch in recording. I'll post all the recordings on Monday. Okay. Basically, radical center is, so I take three circles and I'm telling you that the radical axis of all three circles are concurrent. And they're concurrent at the Lavish, if you're talking about the problem, tell in personal chat. uh, they're concurrent at the point which is known as radical center. The proof of this is take axis of two circles and you get these two equations. And these imply that the point should lie on the third radical axis. So that's all about the radical center. And now I just told about a degenerate case when the radical center does not exist. Or it can exist at the point at infinity, but we are dealing only with the real plane. So it's like when all the three centers are collinear. In that case, the radical axes are perpendicular. Sorry, perpendicular to the same edge, so all of them are parallel. So they don't intersect in the real point. Okay. So, yeah, this is an annoying case that you have to deal with. Okay, try to prove this on your own. It's a homework, it's not very hard. It's just like you have to deal with some edge case. If for a point P, PA times PB equals to PC times PD, such that PAB collinear and PCD collinear, and P lies on both AB comma CD segments or on neither. This condition is important. It seems useless right now. Then ABCD cyclic. So it's a bit like you have to take care about the details, but it's not very hard. Like we have seen all the ideas. Okay. So, okay, is there any doubt about power of point, radical axis, radical center? Uh, Please don't ask me to go over the lecture again. But any doubt which can be clarified in like 5-7 minutes. So, if not, then we'll move on to problems. Uh, don't take the proof for this right now. Not interested. It's detailistic. It's not hard. Solve it on your own.
What does P dash C dash P mean?
This thing.
Yeah.
So it's a notation like XYZ usually means points XYZ are collinear.
Oh, okay.
Used very frequently. Okay. Please raise hand if everything is clear and you don't have any doubts as such. Obviously, it will take time to digest, but you think that everything makes sense for now. Okay, I'll wait for at least 9 people to do it. Expectations are high from the class. 4 people, five people. Like keep your hands raised if you're going. Okay, I see 7 people. 2 more people, then we'll continue. Okay, only 6 now. 8 people now. Okay, 9. That's amazing. Did Aman also raise hand? Okay, that's 9 then. Cool. Oh, pretty great. Very happy that the class is active. Okay, so we'll move on to problems. Who asked me for problems? Aditya, that was you, yes. So we are doing problems. Okay, let me recall this problem. I actually forgot this problem. Okay, very basic problem, like basic in the sense that we have already seen it in the class, like some way of it. So you should be able to do it. Take two circles, omega 1 and omega 2, and Like these are the circles such that A lies on their intersection and they're tangent to the line BC in triangle ABC. Prove that if P is the other intersection, then AP bisects BC. If you're done with the solution, please type in private chat. Oh, by the way, Aman, did you write Lamau last year? Did you solve the geometry in that? Try synthetic. If you don't know the solution, here is the problem. Oh, you know it. Okay. Okay. So one, two, three. Three people are done. I'm waiting for a few more people to do it. Do you actually need a problem to do, Aman? Since you're in the class. I mean, I don't think I have problems for you. Okay. Yes, Aditya, you're also correct. I have not done that problem. It was a buffer problem that I gave to people. So for people who knew POP, by the way. Okay, any more people who have done the problems? Or done this problem? Yeah, Aditya, go on. Okay, what is that? Uh, okay. Someone who has not done the problem, can you raise their hand? We'll try to do the problem together, like in an interactive way. Anyone who has not done the problem. Okay, Swasti, we'll do that. Just a second. Aditya, your idea is correct. I was also trying to do the same thing because then you get some nice things. But I don't actually see how that works. But that is a good idea to consider. You can try to work on it. It's possible I didn't see it myself, but it's a generally good idea. Okay, Swasti. So, what are your ideas? Like, what would you try in this?
So I was thinking we can join the centers of the circles, maybe.
Okay, one second. Let me turn off the power. Okay, so there is an idea to join the centers because obviously radix is nice with that, and you get that the centers are like perpendicular to this thing, right?
Yeah.
But like, it doesn't really help. The reason is it feels too unrelated to the triangle ABC, at least for now. Like the point P in general is nice. None of you would know about it right now. But so the circles ABP and ACP are actually nice. But at least right now, when we don't have any information, O1 and O2 feel very random to add. Just because they're not connected with ABC at all. Like you don't even know where they intersect the segment AP, right? For now,
Yeah.
they intersect midpoint, but you mostly don't know about it, right?
Yeah.
So rather than introducing this point, we can introduce AP cap BC. Let's call it M, right?
Okay.
Can you tell me something nice about M? A question. So the question is, you have ABC triangle. P is a point such that APB and APC are tangent to BC. Prove that AP bisects BC. Okay. Yeah, Swasti, can you tell me something nice about M?
Not sure.
Try to take a random guess. Like, M lies on BC, so MB and MC are tangents, right?
Yeah.
What else does M lie on?
M is on AP.
Yes. So we have M equals to AP cap BC. We have interpreted why lying on BC is good. Why on AP? Like, is there anything nice about AP?
Just to confirm, P is the intersection of omega 1 and omega 2, right?
Yes. So what about the line AP? Like, we're discussing about the line AP. Is it a nice or bad?
It's the radical axis.
Yes. So AP is radical axis of omega 1 and omega 2.
So we
So
know that
this
the
means, yeah, go
power
on.
of M with respect to omega 1 is the same as the power of M with respect to omega 2.
Amazing. What is this thing?
It's going to be
Like, there are multiple ways to write it. MO1 square minus R1 square, MP times MA, or MB square, because
yeah.
MB is tangent. What is the nicest way to pick? Like, what is most relevant to the problem?
MO1 squared minus R1 squared.
No. What do you have to prove? What is the question that you have to prove?
Oh wait, yeah, we can just do MB squared is equal to NC
Yes.
squared.
You just have to prove like M is midpoint of BC. That's the question, right? So we can just directly take the lengths involving B and C. So that gives you MB equals to MC. And you're done, right?
Yeah.
Okay. Did everyone understand this proof? I turn on the fan. It's for. Yeah. Also, thank you, Sasti, for speaking. Yeah. So did everyone understand the proof? Okay, one person said yes. Swasti, I assume yes. Only two people. If you have questions, feel free to ask. Okay, I assume it's clear then. Okay, let me find another question. Okay, this should not be a hard problem. Okay, for people who are curious, Aman, if you're there, please correct me if I'm wrong. It's fine if you don't know, but P is a Humpty point of triangle ABC. Enthusiastic listeners can look up what Humpty point is, what are its properties. It's a nice point. For people who don't want to know right now, it's fine, not very relevant, but just a nice fact.
And A is
Wait,
empty point of
follow up again?
PVC.
Huh?
Never
Wait, what
mind.
did you say? Aman, couldn't hear you.
Oh, I was saying A is empty point of PVC. Like it's true for the other point as well.
Oh, like if P is Humpty of APC, then A is Humpty of PVC?
Yes.
Oh, I did not know that. Feel free to ignore this if you are not very curious, but also feel free to look it up later if you're curious. Antipode of what? I don't. No, no, that's not Humpty. Okay, so let's move on to the next problem. You have 4 points: A, B, C, D. All of them are collinear. You take the circle with diameter AC. So hard. I have a better idea. So you have 4 points: A, B, C, and D. And AC and BD are diameters of the two circles. Let's call them omega 1, omega 2. Let this be X and Y. You pick a random point P on this segment XY. And this point is Z. XY intersection BC is Z. Um, Intersect CP with omega 1 at M and BP with omega 2 at N. So prove that AM, DN, and XY are concurrent. Oh, I think I've heard something similar to that, Oman, but I did not know that. That's nice. Where did you read about that? How people try this problem? Like, feel free to tell me any ideas in the personal chat as well. Okay, this is the problem in front of us. Any ideas, people?
If we can show that the point at the point K,
We can
which
show what?
we let the point K intersection of AM and XY, and then if we
Okay.
can show that K and D are concurrent, K and D are collinear, then I guess we'll be done.
Okay. But you can do, like, there's a much easier way to do this thing. Like, think about more things. Like, that's a very basic way to do concurrency, but maybe think about in power of point terms. Like, it's fine that you haven't spoiled the idea, but that's how you learn about it, at least initially.
Can we try and use phantom points?
Can we what? Can we try what?
Phantom points, like
You're thinking maybe too complicated. Like, okay, maybe too simple. Think more. Like, think something from the lectures that we have done. Like, what could you possibly do to prove this concurrency in one step?
So, sorry, but is P the Mikkel point of AB and the AD and the intersection point of the AM and ND?
Oh, you want me to name that point?
No, is it the Mikkel point of AD and yeah, ADX?
Of Mikhail point of what?
ADX. X is the intersection point of AM and ND.
Can you like type what you said? Like, what is Mikhail point of what? Like, I just understood Mikhail point. Nice. Is P the Mikhail point of AD and C? C is AM intersection. AM intersection BN or DN?
Sorry,
I
AM
mean,
intersection DN.
like Mikhail point is point for 4 points and not 3 points. So, okay. See, so if we prove that, okay, see the circles that we have. We have omega 1 and omega 2. And we know that radius of omega 1, omega 2 is xy, right? So this line is involved already. Now I need to involve AM and, oh, sorry, I just stated the, like, I mean, I stated the question correct. I wrote it wrong. It's DN, not DN. Obviously, that makes no sense. Anyway, so radius of omega 1 and omega 2 is xy. Now, if we can find, like, if AM and ND are radius of omega 1, and let's say some circle called gamma, and see omega 1 obviously passes through A and M, right? So if we can find some circle gamma such that its radical axis with omega 1 is AM and radical axis with omega 2 is ND. So then if we consider the circles omega 1, omega 2, gamma, you have omega 1, omega 2 का radius is xy, omega 1 gamma radius is AM, and omega 2 gamma radius is ND. So by radical center, you are done. Right? So you just need to prove. Okay, see now gamma should have AM on it and ND on it. So you need to prove AM ND cyclic. Like if I prove this, then I'm done with the problem. Right? So now I have reduced it to like an angle chasing ish problem, proving AM ND cyclic.
Could you draw gamma, like the circle gamma, how will it look like?
Can you repeat?
Like how will like circle gamma look like? Can you draw it?
Let me turn off fan. Yes, repeat.
Yeah, like can you draw the circle gamma? Like how will it look like in the diagram?
Very bad, but okay. Like it's just a circle passing through all these 4 points, no? Oh, I see your question now, Aditya. Uh, I'm not sure if they're actually cyclic. I don't think so they are cyclic.
Won't BCMN be cyclic?
Yes. So, okay, can you tell me why? So we have a claim BCMN cyclic. Okay, see, first of all, you will see that these three lines, BN, CM, and XY are collinear. So this already motivates something like two lines are concurrent on the radical center, right? So this is a theorem in EGMO, but I did not want to state it explicitly because you should be able to come up with facts on your own. So if we see the point P, right? P lies on radix of omega 1, omega 2, right? So power of P with respect to omega 1 equals to power of P with respect to omega 2, right? What is the power of P with respect to omega 1? Someone except Lavish and Uma. Aditya, I don't know. Like the only cyclic quadrature in the figure that you have is CYMA, not ZPMA. I don't know if that's cyclic. Very likely it's not as well. Unless you can prove it to me, which is fine. Oh, it is cyclic. Is it? Give me a second. Okay, yeah, ZPMA is cyclic. But I don't see a way to involve Z. Like Z is as good as line XY. So yeah. Yeah, now since ZPM is cyclic, ZPND is cyclic. Okay, I'll tell you why this is cyclic. He's saying that you see that this angle, angle AMC, this is 90 degrees because AC is diameter. And this is also 90 degrees because XY is radical axis. So you have that ZPMA cyclic and you have ZPND cyclic, which means PMN and this intersection point here should be cyclic. And now you have to show that P, Y, and that point is like collinear. Maybe you can angle this and finish off. Like now this looks plausible because you have PM and that point is cyclic. Maybe we can do it that way. You should try it to finish Aditya, definitely. But I'll motivate some other solution which has another idea essential to the class. But yes, very good idea.
Like, do we involve the center when you're talking about like power of P in respect to omega 1?
No, see, the thing is, centers are bad. Like, there is no use of involving center practically because we are not even dealing with segment AC or BD individually as such, right? Like, center will lie on those segments. We know that for sure, right?
So kind of like the radius are like AC square by 4, like AC by 2 whole square, something like that. Like,
I
will that
mean,
be
you
helpful?
can, but that's not very helpful. Like, AC has no role as of now. Like, okay, there are other ways to write power as well, right? Think about that. What is the other way that you can write power of P? Like, there's a reason I motivated all that thing rather than just giving the formula, right? Because formula is not that significant usually. How can I write power of P with respect to omega 1? Yes, that's the correct way to do it, others. But there's another way which is better for us.
Oh, like PX times PM and PM and PC, you mean that one?
Yes. So see, like P passes through this chord XY. So I can write it as PX times PY. Or like PX, like X and Y are obviously I know rad X, so not typical. See the other chord. I know MPC, right? So I can write it as PM times PC. Excuse me. Because both of the points lie on the circle, right? Similarly, I can write power of P with respect to omega 2 as PB times PN, right? Sharaina, is this clear?
Oh yeah, yeah.
What does this give?
Yeah. That's just like PM radial axis.
BCM and cyclic.
Yes. Like you can angle chase to show this as well, right? Like you'll get PBC triangle similar to PNM by length, and then you'll have angles like this angle equals this angle. So nice others. So this means BCM and cyclic. Essentially what our claim was, right? So is this clear to everyone? Like why BCMN is cyclic and why this was not okay. The motivation is you see that P lies on the rad and there are a lot of segments passing through P. So maybe I use the fact that P lies on the rad somehow. And it's not very hard after you think of that thing to get BCMN cyclic. And it's a nice fact. Like I suggest after this class, read ECMO, things will be clear to you. You'll see much more things. Chapter 2. I think that's public. Chapter 2. From what I remember. Okay. So now I have BCMN cyclic. And I need to prove ADMN cyclic. How do I do this? Like now it just feels angle chase. Like up to angle chase, you have so many circles. Fine. So basically, I need to prove that I forgot myself. Let me think.
AM and D are cyclic.
I know. I mean, I know what AIM and D is. Like, I need to prove that. But how do I prove that? I forgot that. Let me think. Like you should also think, obviously. Hmm. Okay, so Let's pick some color. Okay, maybe this color. See, let this angle be equal to alpha, right? Then this angle is 90 degrees because BD is diameter. So this is 90 minus alpha. Since BCMN cyclic, this angle is alpha, right? And this angle is 90 degrees because AC is diameter. So this whole angle is 90 plus alpha. And now angle AMN plus angle ADN equals to 180 degrees. So we are done. Is this clear?
Yes.
Okay, I'll just quickly go over the proof once more. So the idea is you see that these three lines are there. First, it's like very symmetric in like A and D-ish thing, right? And you already have like one radix involving the concurrency. And we see that radical acts like radical center thing is a very nice way of proving concurrency. So I'm like, okay, if I can find some circle which have AM and ND as another two radics, which can provide me that, then I'm done. Which means I just need to prove AM and D cyclic. Then I use the fact, like you can do this earlier as well, whatever order doesn't matter. That okay, P lie on the radix. What if I use that fact? Power of P with one circle equals to with the other circle. And then you represent it in a nice way to get BCMN cyclic. So now you have BCMN cyclic and you need to show ADMN cyclic. It sort of looks true by something like symmetry, intuitively, not very obvious. So you try to prove it. And then you are done. So that's the basic proof idea and motivation. So is that clear to everyone? Like raise hand, ask questions, thumbs up, anything.
Hey, I was also curious about the proof that the other guy told. What was the proof he showed? Na Z Z
Okay,
E N.
so right, I'll tell you about that. I'll do it on GeoGebra because it's too much work. So let's say I have right. So this is the problem basically. Uh, You need to prove these three things are concurrent. So what we said was, if this point is like Z, notice that this angle is 90, right? Angle CMA, because CA is diameter. And this angle is also 90 because AZP, like XZ, XY is radical axis, and this is the line joining centers. So you have that uh, A, M, PZ cyclic. Similarly, you have Z, P, and D cyclic, right? which means if I let AM intersection DN, let's say K equals to intersect line AM and line DN, then PM KN should be cyclic, right?
How this
Okay,
90-90.
I'll give you a small exercise.
It's 90, right?
Wait, I'll just come on this thing once again. Oh, in that thing it's 90, but general exercise, you should do it. ABC is a triangle, some random points, D, E, F. Prove that the circles ADF, BDE, and CFE concur.
Equal point, no?
Huh?
Equal point.
Yeah, so that's what we did here, no? Same thing.
Oh yeah, okay.
Like you had the triangle AKD. Take M and Z to be the random points. So you have AZM, DZN. So you get P. So KM and P. Right?
Okay.
So
Yes,
now
yes.
you can rephrase the problem like you have P, you have M, you have N. You introduce this point K as like PMN, cap, AM, and DN something. And you have to show that PYK, like PY and K are collinear. Maybe you can angle chase it somehow. I don't know how, but maybe you can. Like it's a nice way to think about. I don't know the
Okay.
finish, but it's a good proof idea, is what I was saying.
Okay, yeah. Okay, got it. Thank you.
So that's it for the class. I'll stop recording. Feel free to ask any question. Okay, no, I'll stop recording after question. There any questions regarding the class, power of point and stuff? Any questions? We'll definitely have a problem solving sessions. If not me, someone else will take it. Feel free to give feedback of this class. If not to me, to Sai or Sanjana, they'll forward the feedback to me. Or you can just DM a man.
Like about the buffer problem, and like, will you share the solution?
Uh, Let me turn off fan. It's so bad.
I just shout my question. It's buffer problem.
Yes, can you repeat now?
Okay. The buffer problem, will you like share the solution?
Oh, buffer problem. No. We'll do it in a problem solving class because you still need to develop more ideas for that problem. At least for the people who didn't know POP before. There are still 2, 3 ideas that you need to solve that problem. Okay, actually one idea, but I mean, it's a buffer problem. So it's supposed to be hard. Try it until the next class. Like I'll maybe add it in P set. I'll ask you to add it in P set. So yeah.